to have clear understanding of our theoretical framework where we can explain networking, today I'm going to tackle two issues. One is to have a reference model, some clear understanding of it, and which reference model we are going to really focus on. Two, we are going to focus on the discussion regarding broadcast domains and collision domains. Therefore, once you have got clarity on those understandings, it is easier to explain most of the generic networking related issues. Okay. Therefore, don't worry, I'm going to use only 3 slides for today's discussion. The first slide is these 3 models. The second slide is the IEEE 802.2x standards. The third slide is about collision and broadcast domain. They are not official reference materials, but they are here to discuss, to guide my discussion as far as these concepts are concerned. I promise for each chapter, I'm going to give you enough materials. Therefore, one of the materials you'll find in the chapter 1 distribution is a clear description about all these models. You are going to have additional materials on the description of collision domain and broadcast domains, and you are going to have also additional materials that helps you to recap networking related issues. One file that I'm going to include in there is going to be the question and answers that I promised. Therefore, when we meet on Wednesday, I'm going to use that file in order to go through the different aspects of networking by bringing up those concepts for our discussion. Then based on that, of course, we can gauge how much we understand about networking. Okay, therefore, as in any concept, you are going to need a reference model. Okay, if you are a religious person preaching, you need some kind of a holy book, whether it is a Quran or a Bible. You are going to need such kind of a book in order to describe or in order to preach the followers on how to act on things. Therefore, whatever you are preaching about, it is going to be referenced into that holy book. Therefore, in a similar fashion, networking should be referenced into some kind of a model, but that model cannot be a unified entity because the very idea of networking is very broad. Therefore, whichever model you are looking at uses what we call a layered approach. Therefore, whether you are looking at 7 layers here in the first one, or 4 layers here in the second one, or 5 layers here in the third one, the whole idea is we are going to need some level of disparity between the layers, but achieving at the same time some level of integration. If you stop explaining networking in that manner, you are going to have monopoly. Okay, have you ever imagined a single vendor is going to provide you the cables? The same vendor is going to give you the network cards. The same vendor is going to give you the TCP IP stack, including IP or ARP, etc. The same person is going to give you the transport layer stack, such as TCP or UDP. The same vendor is going to give you any kind of issue, such as SSL or SQL or HTTP or DNS. If all of these are going to come from a single vendor, you are going to end up in a problem. It is going to be antitrust. It is going to be monopoly. Therefore, the whole idea of this model definition is, let's provide the overall general functionality. Then vendors can actually excel in building the different components of that particular functionality. Therefore, the models are there to explain functional descriptions. They are not going to be product specific. They are not going to give us any kind of leverage, in detailing a specific product type. Okay. Therefore, we need to have a mechanism to explain whatever device we are having based on its functionality in such a way that whatever achieved by that device is going to be explained by that reference model. Therefore, unfortunately, you need to remember most of the theory here. Of course, your reading materials are going to help you. Our discussion is going to help you a lot. But whenever we come to each of the chapters, we refer back to these models. Therefore, the very first model that has been created is from ISO, the International Standards Organization, and it is called the Open System Interconnect model, or the OSI model. And the OSI model is really, really an old model. Okay, it is like more than 40 years old. And of course, through time, yes, it has been explained a lot, it has been described a lot, but through time, there is some level of redundancy. Therefore, now keep in mind, we are using this model here, the hybrid model, as the reference to all of our discussion from this point onwards. Therefore, all our discussion is going to be guided by this. But the definitions that you are going to make yourself familiar in the other approach, most importantly in the OSI model, is going to be still applicable on here. Therefore, now let's try to give a very broader definition of what is explained in these layers. Okay. Therefore, as you expect, on top of here, okay, and down here, we are going to have two important components. Up in here, we are going to have user programs. Okay, and don't confuse them with applications. Many references are confusing it with application. Application has got its own role. These are protocols that are being used in order to interface user programs to the network. They are not full-fledged applications themselves. Then down here, we take for granted what we call generally communication engineering. Communication engineering. Okay? Sorry, 1 minute. Sorry, guys, some interference from children. Okay, therefore here down here, you do have communication engineering. Therefore, we take for granted. None of us are actually worried about how data is being transferred in a glass in fiber optic cable. None of us really bothered about how to know wireless signals propagate from our mobile and reach a cell tower. Okay, most of it is, of course, going to be described in the physical layer details, but there is a lot happening at the communication engineering level where we are taking those things for granted. Therefore, the whole concept is, at the end of the day, how can we enable these user programs entertain the network infrastructure here? Okay, so let me give you a very brief definition regarding each of them. Okay, therefore, let me begin at the physical layer, as the name implies. Therefore, when you are really focusing on the physical layer, this is actually focused on about bit transmission. Okay, that is the whole context. Now, when I say bit transmission, you are going to really focus on issues. What is a bit at the end of the day? Okay, have you ever imagined? There are two types of signals. The entire computer industry, the entire computer networking, including the internet, is actually running on the digital realm, but there is also another two signaling called analog, okay, another counterpart. Do you have any kind of understanding of that? Anybody volunteering to explain the difference between analog and digital? Either you can raise your hand or you can unmute and speak. Any volunteer? No volunteer, okay. Therefore, let me try to look into this. Okay, if I ask you a question this way, can you transmit anything via a network? Okay. Yes, Mr. Gorgis, thank you. Please go ahead.
Hi, Doctor. ይሰማል?
Yes, ይሰማል.
I guess ልዩነታቸው I mean the difference between bit transfer and analog I guess bit transfer uses the technology of transistors, where make use
Okay.
of zeros and ones,
Okay.
whereas the analog system uses some other thing, a technology before, I don't exactly remember, a technology before the transistor
Mhm.
that transfers only limited amount of information, kind of,
Mhm.
yeah.
Okay. Nice thing. What is the meaning of the English word analogous?
Uh,
Something is
manual,
analogous. If we say the word analogous, what is the meaning of it? It
uh,
means similar, አይደለ? That is the word.
yes.
This is similar to what we taught. Okay. Therefore, let me try to assist you in that regard now. Whatever you are trying to carry over a network, it should be represented. For example, think of me speaking to my computer. What kind of energy my mouse is generating? Voice energy, okay? But in order to have my voice transmitted and reaching your computers, which network infrastructure we are using? The internet, yeah? But before it enters the internet, my voice should be converted into some kind of a signal. In this mode, an electric signal. And who is responsible for converting my voice into a kind of signal, electrical signal, which can be recognized by my computer? It is called a microphone, isn't it? And what is converting my voice in your side into an audible entity? A thing called a speaker, yes? Therefore, in chapter 2, we are going to look into a normal mode of communication. Therefore, what is happening is you are going to have the original signal. Maybe let me stop sharing here. Let me use the whiteboard, okay? Therefore, now you are going to have source information, and that source information can be anything. It's a natural thing. It is like my voice, it is like weight, it is like temperature, it can be anything. And our argument here is anything can be processed by a computer. Our argument here is anything can be sent via the network without any problem. If you are asking some person, let's say 200 years ago, they will tell you voice should be only communicated via air in the presence of a mouse and an air. Then someone who is living 120 years and downwards is going to tell you, of course, we are going to use a telephone to communicate from one point to another. The telephone has got a microphone and it can be carried over wire or wireless mechanism. Okay. If you are living, let's say 200 years ago, you don't go to the where you are going to do some photo shots at a studio nowadays, yeah? In the old days, you are going to sit in front of a person and they are going to draw you. Of course, they are using their eyes. And in effect, it inspired someone to invent a camera, to invent a scanner, so that what you see is going to be somehow converted into another format, such as electrical signal, and that electrical signal is going to be stored and processed by any kind of mechanism that you are having. Okay. Therefore, here the source, it can be processed as it is in a normal scenario. That is the issue. I have, let's say, a kind of sound, and if you notice my sound, okay, it is like this. When I start the class, let's say I'm creating an axis like this. This is the pitch of my voice. This is the time of our class. When I begin, I'm slow. When I'm getting better and better, I'm getting some kind of, okay, erratic nature. Then in the end, I'm going to have some tiredness. Then at one point, I will stop and go away. When you look at this particular signal now, you see a very erratic nature. You don't see any kind of uniformity, plus there is some level of continuity between this point and this point. And as you all know, if I ask you how many integers are between 0 and 1, your answer is directly 0, because there are no integers between 0 and 1. But if I ask you how many real numbers are there between 0 and 1, what is the answer? Anyone? You can interfere.
Infinite.
How many? Infinite. Therefore, at the end of the day, you are going to have infinite numbers. Therefore, now, which one has a good luxury? Is it better to worry about infinite things, or is it better to worry about these two endpoints without having anything in between? This definitely has got its own luxury. Okay. For example, if I'm punching you on your face, and if I punch you every 1 minute coming back, okay, you have got all the time to run away or fight back. Then what if I punch you uncountable times, maybe 100 times between that minute? What is your rate of reaction? It is going to be very limited. Therefore, in a similar fashion, if something is analog, always keep in mind this is a definition. Analog means, okay, a signal which is continuous in time and value. That is the whole definition. Okay. Therefore, it has got two things in it. The first thing is focus on signal. Signal is a kind of synonym for something you can represent. The very known signals are electric signals, optical signals, magnetic signals, electromagnetic wave signals. At least these are our most important things. Therefore, if I have a voice, let it be one of them. If I have a picture, let it be one of them. If I have a temperature, let it be one of them. Therefore, all the things that we have needs to be represented in a kind of format which is understandable by the machine. That name is called a signal. Okay. However, that signal is continuous in time and value. What is the very meaning of continuous? Continuous means, this is the direct definition, infinite possibilities. Okay. This is the overall encompassing. Continuous in time and value. Now, if you look into this particular signaling in detail, earlier Betragorgis brought the idea of transistors, because transistors are the bedrock of any digital things that you can think of. But what is the most important thing about transistors? They understand two states. Okay, they have got what is known as saturation and cutoff, and they understand only two states. Therefore, in two states, you are going to have only two understandings. Of course, mathematically, you can call them 0 and 1, but that understanding can be explained in two states. Therefore, something infinite versus something two states. Therefore, if you are worried about infinite things, for example, let me give a very simple scenario. Which one of you are listening me absolutely now? How many of you are 100% with me now? Okay, let me ask myself also. Am I 100% with you? No, I have got bits and pieces. Yes. Therefore, there is some kind of thinking happening. There is some kind of distraction happening, but I still manage to transfer what I try to transfer to you. Therefore, I don't need to be absolutely present. Why? Infinite means you are going to be fully there. Is there error correction? No time for error correction. Is there error? No time to sense errors. What is happening if you are communicating in analog? If you are processing in analog, you are at the mercy of the entire environment. You don't have any kind of manipulation. You do have very difficult storage. You do have very difficult processing. Above all, you are going to have a very complicated communication. Communication between one point and another point. For example, if I send you this, let me stop the share and open it. Okay, for example, look at this. You have a source. This is the signal you are sending. Okay, then here there is one thing that we call a bad guy. That bad guy is called channel. Okay, therefore now if you have a channel, the channel has got an effect. What is the effect? It is going to affect your signal. Now the destination receives the following. Receives this. Okay, therefore this is T1 time T1. This is beginning of time 0. This is beginning of time 0, and this is end of the transmission T1. Now let me raise a very general question. Can you see errors here? Can you see errors? Any volunteer? Because straightforward it is. You see errors, yeah? Because what has been sent and what has been received are not the same. Okay, who is the culprit? The channel. Now, what if I make things really amplified enough or powerful enough to win the effect of the channel? Maybe I will get some other different signals. But if you look from the point of view of looking at both of them, there is an error. And how much error is there? How much error is there? You have got infinite representation, and how much error you are having here? Infinite errors. Therefore, can you correct this? No. Can you even know there is an error? No. Therefore, as a recipient, you are going to be at the mercy of the sender. The sender should amplify. The sender should magnify in order to win the channel. A simple example, can I kill you with a bullet by throwing using my hand? I can't, yeah? Whatever force I'm having, I cannot throw a bullet and that bullet pierces through you. It's impossible. But how can you give a big kinetic energy to the bullet? You can use a gun. What is the secret of the gun? It has got a powder, and that powder is going to accelerate the bullet to the extent that it is going to pierce through some material. Okay. Therefore, now the channel is the material, but the effect of the channel is degraded thanks to what the source does. Therefore, as a communication entity, you are at the mercy of the sender. This communication existed for so long, this processing existed for so long, but it is not sustainable. You cannot use transistor-based or IC-based or generally computer-based technologies here. Therefore, what is the solution? The solution is to use digital. Okay, I don't want to sophisticate these things. If you are interested, I will give you notes, but in chapter 2, I will come into such discussions again. Therefore, digital is a sample, okay, remember that, huh? Okay, and quantized and two-state representation of an analog signal. This is the definition we are having as far as this course is concerned. And all in all, our networking is end-to-end digital. Okay. Therefore, what is the problem with analog signals? Infinite nature. Where infinite nature? Everywhere. In time as well as in value. Therefore, what can we do now? We can do the following aspect. Okay, let me delete it. Sorry. We can do some aspect. How can we change the time continuity into okay, a discrete value. The time infiniteness into a discrete value. That process is called sampling. Once you sample a particular signal, you are going to change again the infinite nature of the signal in value to discrete entities. Okay, that process is called quantized. Then you don't stop at that level of discrete quantization, but now you are going to change that into two-state. The whole idea of two-state is binary. The other name of two-state is bit. The common name of bits is ones and zeros. Okay. Therefore, there is no natural digital signal. There is always natural analog signal. As the word implies, analog signal is analogous to the natural entity. However, since we cannot use computers to process analog signals, we are going to change it into a digital data. Therefore, when I teach you networking, I'm teaching you about end-to-end binary data, end-to-end binary value. We are not focusing on any kind of analog representation. Therefore, that particular layer I focused on, the physical layer, is going to be focused on bit information, binary information. I hope you have got that clarity. And in chapter 2, I'm going to come to the discussion of how you can convert analog to digital. And maybe if you are really want some level of advancement, we can actually focus on how to convert digital back to analog. But there is some mathematics depending on it. We are going to talk about periodic signals, non-periodic signals. Then we are not going to go deeper because that is more of engineering, but I'll tell you a lot about those aspects in chapter 2. Therefore, as far as we are concerned, we are using a computer to network. We are not using an analog device. Due to that reason, what you have should be ones and zeros. This much is enough now. Therefore, going back to the PowerPoint presentation. Therefore, now, here at the physical layer, I think I missed my annotation. Here at the physical layer, we are actually focusing on bit transmission, ones and zeros. Okay. You guys are listening me now. What is coming to your mind? Sorry, what is coming to your ear is my sound wave. But at the end of the day, you are going to process and understand the meaning of what I said here at the user program level, at the application layer level. Therefore, if you go up, you are going to have machine understanding decreased. Okay, let me use a pointer, just a pen. Therefore, if I go up, human understanding increases, machine understanding decreases. If I go down, machine understanding increases, human understanding decreases. Therefore, in all your different courses, for example, how many of you tried programming a particular drive, a particular processor using switches? I hope none of you were born at that time. Okay. Maybe, for example, you do such kind of programming every day in your life. One good example is switching on and off a bulb, a light bulb. When it is night time at your home, you are switching on and switching off a light using a manual button. You know? Imagine your programming looks like that. It is totally sophisticated. Therefore, none of us are actually doing programming by connecting wires and disconnecting wires. Okay, was it a reality? Yes, it was a reality. If you read the stories, if you Google about UNIVAC, ENIAC, etc., the old computers, that was the story. But is it a very nice form of programming? No, it is really bad. But most of you have also tried some kind of assembly language programming, low-level language programming. Okay, is there anyone who can tell me what is so special about assembly programming? ለትረጎርጊስ የቅድም እጅን የተነሳው ይመስለኛል አይደል? Or are you raising it once?
የቅድሙ ነው ዶክተር።
Okay. Anybody who want to say something about assembly language programming, lower level programming? I'm not teaching you about that, but I want you to have that level of comparability. Okay, one fact about assembly language programming, it is machine related. It is related to a specific processor. For example, you can have assembly language programming for Intel Pentium processors, or Intel this kind of processors, or AMD this kind of processors. Due to that reason, you need to master so much computer architecture. You need to understand the registers of the processors. You need to understand the machine language of the processor. Even if you are using something that looks like English-like instruction, it is going to be so difficult because your knowledge is attached to a single machine. But can you now imagine there is a network that you are building only cater for health application? Then you are going to have another network which only cater for educational application. And you are going to have another network which is going to cater for music application. Is that a possibility? No. The network should gather, okay, or somehow support the idea of supporting everything that comes into it. Okay. Therefore, now synonymously compare it with high-level programming language. Therefore, high-level programming language, thanks to compilers, thanks to assemblers that are underneath them, you can have no problem of worrying about the machine you are programming on. Even some programming languages are helping you to do non-operating system dependent programming language by creating such kind of a platform. Therefore, the entire network is application agnostic. At the end of the day, when the application reaches that wire level, that wireless level, it is going to think about bit transmission, therefore ones and zeros. But ones and zeros are not going to provide a meaning. We need to do some level of meaning. Okay. I am saying words themselves are not enough to make myself clear. They need to be combined into sentences. And sometimes my sentences need to be combined with other sentences in order to form a paragraph. But at the end of the day, if you are your ear simply says there is some voice coming. Okay. If I speak a different language now, your ear will say, I'm hearing something. Yes, the signal is there. But your mind is going to say, oh, I don't understand this. Therefore, going up, there must be a clear understanding. Therefore, at the data link layer, you are going to worry about another level of data management. Okay, you are going to worry about frame assembly. Okay, you are going to worry about media access. Okay, you are going to worry about hardware address. You are going to worry about any kind of logical link control. You are going to worry about such kind of issues. Now, your thought is a little bit becoming more human friendly. In a sense that I'm not going to be bothered about ones and zeros, but rather I'm going to be bothered about a collection of ones and zeros. Generally, this is called network technologies are used to deploy this, okay, such as Ethernet facilitates this, okay. Therefore, things like Ethernet, things like token ring, things like ATM, things like frame relay, things like X25, All these kind of different network technologies, they are going to facilitate the ideas over here. Therefore, this is the base. This is the base. This is like the hardware where your computer is going to live on. Sorry, your network is going to live on. Therefore, this is like the computer where the rest of the network is going to be live on. Due to that reason, these two layers are implementable. These two layers are not configurable. Okay. Yes, someone can fake the MAC address, but it is some software manipulation at a higher layer. Yes, you can say instead of Ethernet, I want to deploy token ring. Yes, you can, but there is no such a configuration that you can do on the network card. You need to change the network card. Yes, you may say, I'm going to have an ATM infrastructure, and you are going to use ATM switch and other related stuff, but at the end of the day, you are going to deploy a technology which is created for that. But as far as our local area network is concerned, you are going to have Ethernet technology facilitating this aspect. Okay, therefore here now, the two layers, they are colored differently here. They are there as the bedrock, as the most important elements of that. Imagine, you need to be born, you need to be a human being, then at the end of the day, you may speak Amharic, or you may speak Afan Oromo, you may speak Tigrinya, you may speak Arabic, you may speak Spanish, or whatever. But first of all, you are going to have that human capacity embedded here. Then the rest of the things that you are going to learn now are going to run on top of it. Okay. If there is no hardware to support all these aspects, you are going to end up in a problem. Therefore, these are the two network technologies that you are going to focus on in order to deploy the bedrock or the hardware aspect that will help you to run a network. Then when you are going upwards, you are going to have additional meanings. For example, here, if you worry about networking, this is all about internetwork, okay, internetwork addressing and routing. This looks a very simple term, but if you ask me to teach you about this, I can still teach you for 1 year because there are lots of issues related to addressing and routing. This is the whole concept of chapter 4. Therefore, internetwork addressing and routing. Therefore, first of all, let's come into this. Even if you have got what I call a hardware address, all of you know it as MAC address. Even if I have got a hardware address, I cannot differentiate the broadcast mechanism, okay, between different devices. I don't have a territory, okay. For example, I'm asking this. I'm talking here now. I want the whole of Addis Ababa is going to hear me. Is that a possibility? No. Each of us has got our own territory. What is so bad about this thing we call broadcast? Later, we are going to discuss it. Broadcast is a very important part of our communication, okay? Broadcast is a very important part of networking. In all my discussions, you are going to hear it from now on. I will never say down is broadcast, okay? Broadcast it fa'anilum. Always remember that. Okay, we are going to say manage broadcast. And the very device that helps us to manage broadcast is called router or any kind of routing device, such as layer 3 switch. They will help us to territorize our broadcasts. However, these devices, they need to guarantee communication between these individual broadcast domains. Therefore, the single broadcast domain is called a network. Another broadcast domain is a network. Communication between these different broadcast domains is called internetwork. And internetworking cannot be facilitated unless you do have a hierarchical addressing scheme. Hierarchical addressing means opposite of flat addressing. Flat addressing does have no reference. I'm looking for Ababa. Ababa who? I don't know. Where is he working? I don't know. Who is his brother? I don't know. What are you looking for? Ababa. What do you consider that guy? It's crazy. Then how many are we now? In this particular group now, we are 23 together. What if I ask you, is Ababa around? I've got an answer. Either يلم ወይም አለ የሚል ነገር አገኛለሁ. Yeah. Why? Because the information is shared among a few of us. But what if you are coming at Bole Airport and you are asking for Ababa? Where is he living? I don't know. Is he living in Addis Ababa? I don't know. Where is he living? I don't know. Where is he working? I don't know. Where is he studying? I don't know. Who you are looking for, Ababa? Do you have his picture? No. Therefore, that's a flat address. Flat address is going to operate if the number of hosts that are using flat address are minimal. Therefore, that territory where end users are going to rely on that flat address scheme defines a network, defines a VLAN, defines a subnet, okay, defines a LAN in most of the cases. Therefore, you are going to have one single network. But the moment you come out of the single network scheme, you are going to rely on inter-networking addressing. Therefore, your flat address thinking is non-configurable. You cannot do anything about it. Hardwired address, MAC address. However, where you belong can be configured accordingly. And the particular famous addressing scheme that give us such freedom is, of course, IP, the Internet Protocol address. IP version 4, IP version 6, yes. Okay, we are going to talk about subnet ID, you are going to talk about broadcast ID, valid address range, all these kind of things in the respective chapters. But the whole idea is, how can we territorize our network? And once we do that, how can we communicate with another similar territory through a concept of routing? Therefore, the very definition here is this one for today's discussion. But again, by far, this particular course is going to expand this little sentence. Okay, that is the biggest chapter we are going to have. Okay, even the revision questions that we are having next class are going to have some ideas related to IP. Therefore, this is networking. Now, up to network, these three layers constitute infrastructure. Therefore, they can be repeated. For example, when I speak now, in order to reach your ear, I'm going through the internet. How many routers I passed? I don't know. But who is providing that routing? Ethio Telecom as the internet service provider. Therefore, I am reaching different routers. And luckily, if I'm using a proper routing algorithm, I'm going to use the best path. Then based on that best path, I'm going to reach the destination. Therefore, these three constitute infrastructure. Therefore, we are going to spend some time in understanding the infrastructure aspect. Therefore, when you come, when going up, these are going to be called host processes. From this point onward, we are going to have host processes. The end parties that are communicating one another are expected to run each of these layers individually on those specific hosts. That host can be a server, that host can be a client computer, that host can be a printer, that host can be a scanner, that host can be any network device. But the network device is responsible for running those layers. Due to that reason, the top 4 layers are actually called host layers. They are running on the host. Therefore, what is happening at the transport layer? A very simple definition is assurance of end-to-end guarantee. Okay, this is really important. Okay, through a number of mechanisms, you are going to read about it. Through, for example, multiplexing, demultiplexing. Okay, encapsulation. You may encapsulate data. so that they can have appropriate understanding. Okay, error control, sometimes flow control, etc. You are going to utilize all these concepts in order to assure end-to-end guarantee. Now, from your future chapters, you are going to see them clearly. But if someone is saying about multiplexing, demultiplexing, I'm focusing about port address. Okay. This is a very simple terminology that I'm going to repeat again and again. Let me say it now for the first time. If you want to uniquely identify a particular host in a single network, if you want to uniquely identify a particular host in a single network, you are going to need a MAC address. Is it difficult? In a single network, you need to come to the point where you need MAC addresses. Point one. Point two, in a network of networks, internetworking, in order to find a host uniquely, you are going to need a hierarchical address. The best example of a hierarchical address is, of course, IP address, but IP is not the only hierarchical address. For example, in IPX protocol, we used to have what is known as IPX number. In any case, if you have multiple networks, in order to find a particular host, you are going to need a hierarchical address. Now, once you find the host, in order to find a specific process in that host, you are going to need a port address. Therefore, port addresses are defined as the transport layer. That's why we do have TCP port 80 for HTTP, TCP port 443 for HTTPS, okay, TCP port 80 for port 20 and 21 for FTP, okay, UDP port 469 for TFTP. All these kind of issues are going to come. Multiplexing and demultiplexing is the reason there. Then you are going to need some level of encapsulation, some level of proper understanding. For example, in our normal day-to-day communication, we can recognize between insult and normal communication. Yeah. Therefore, that understanding comes because you understand the language. But what if I said some words in a language that you never heard of? We cannot communicate one another. Therefore, that is the kind of concept. But UDP is going to have a simple encapsulation. TCP has got a very sophisticated encapsulation. But in the end, tries to answer two network needs at this layer. Don't worry, this is a very general introduction. Each of the chapters will come. And if the general introduction takes your mind a little bit around there, that is my intention. You know how to raise the questions afterwards, okay? Therefore, there are two network needs. The first network need is called delivery guarantee versus performance guarantee. Okay. Of course, the best example of performance guarantee is implemented by a protocol called UDP. And the best aspect of delivery guarantee is implemented by a protocol called TCP. Therefore, in its sense, this paragraph here captures the whole essence of chapter 5. Okay, how can we deal with all these issues? Without that, there is no network. Okay, without that, there is no network. Keep in mind, if anybody is arguing with you, this is my say. Out of these 7 layers, there are 3 that you cannot live without. If you are talking about networking, there are 3 that you cannot live without. Physical layer, data link layer, and transport layer. Without these 3, you cannot live. Otherwise, you cannot have any kind of networking concept. You can live without a network layer if how many networks you have? Only one network you have. You can live without routing. You can live without hierarchical addressing. Okay. And if you are good enough in programming, you can totally avoid what is provided by these layers from some protocols such as TCP IP. You can do the programming yourself, and you can actually interface your program to the transport layer. Therefore, the three layers that you cannot leave is something running in the host and something being provided as an infrastructure. Okay, then I'm not going to waste your time to deal with all these issues, okay, because we have a full chapter, but at least notice that this is a host process running on each individual machine being any computer or any related thing, then it is going to provide this service. Okay, good. Then the other aspect, this is a redundant layer, I have to say it beforehand, because it is also done by transport layer. Okay, maybe from your previous discussions on networking, you heard about TCP. TCP is a protocol that guarantees delivery. Good. How can TCP guarantee delivery? Before it sends anything, it does session, or it does establish a connection through a process known as handshaking. Once that handshaking process is ended, maybe in your prior discussions, you may have heard about flags of TCP, SYN, ACK, and ACK, and that synchronization process is going to guarantee the connection between TCP host sender and TCP host receiver. For example, our class begins at 2 p.m. Taye and David were there on time at 2 p.m., but the rest of you came a little bit after 2 p.m. That's really wonderful, no problem. But what if I started the class exactly at 2 p.m.? That's going to be really bad, yeah? Okay, I need to wait at least a few minutes. I think we waited you for 12 minutes and we started. Therefore, that 12 minutes gave me the kind of assurance that the majority of my students are now connected. Then once you are connected, of course, we establish a session. Once that session is there, we are not going to lose what we have been communicating one another. That is how TCP does. Therefore, session is a very definition of here. The session definition is managed conversation. I have to say that. Okay, a structural query language for database, or if you think about automated teller machines in the bank, communicating with your backend core banking, or if you are thinking about TCP, there is a high, there is a delivery of information, and there is a buy. Therefore, that is managed conversation. However, managed conversation can still be facilitated by some protocols as a transport layer, or managed conversation can be pushed into a user program itself or an application protocol. Therefore, this is redundant. That's why you don't see it at the hybrid model. You don't see that at the hybrid model. Okay. Therefore, that is very much redundant. That's why it has been taken away. Then presentation focuses on the issue of formatting. Okay. Therefore, here data formatting, including encryption, if there is any, and compression. And again, imagine I'm showing you these 7 layers here, and use your common knowledge. This is like a ladder, yeah. And if you come to the hybrid model, or if you come to the TCP IP model, the ladder makes real sense. You cannot go to data link without first stepping on the physical. You cannot go to the network layer without first stepping into the data link layer. Therefore, that stepping as a ladder makes sense. No problem at all. But if you are here looking at the OSI model, the session layer makes things difficult because it has been done by others as well. Now the same thing is true. Presentation layer, the data formatting aspect, including those encryption and compression aspects, is very usually done by the people or the user programs, okay, that are actually done here. Can I mute you, Huawei? Or if you have a question? Okay, thank you. Therefore, here, think of like this layer is facilitated by user programs, most importantly. And in few rare scenarios, you can have this facilitated by application layer. Session, TCP can handle it. Session, application layer protocols can handle it. Most SQL language, database language. Session can also be handled by user programs. Due to that reason, they are considered redundant. That's why you don't have in the revised models, you don't have those things. Okay. Therefore, what is happening at the application layer? Let's give that definition. Okay. Here provides protocols that provide network services to user programs by hiding lower layer complexities. What are those? Give me an example of a user program, Internet Explorer or Edge or Chrome or Mozilla, isn't it? You can use Chrome for web browsing. Who is that protocol facilitating web browsing for you? Okay, HTTP or HTTPS. Those are the protocols. And always remember this. What is the speciality of, let's say, Chrome? To execute server-side codes into our client machine. Whether it is PHP or .NET or whatever web code or Java that you are having on the web server is going to be executed on our front end. That is the purpose of Chrome. If you expect Chrome to understand networking, if you expect Chrome to understand bits, if you expect Chrome to understand routing and inter-network addressing, etc., forget it. Chrome is going to really suffer a lot. Therefore, what does Chrome do? It delegates that to this protocol. Therefore, protocols such as FTP, okay, protocols such as TFTP, protocols such as DNS, protocols such as DHCP, all of them are actually provide such functionality. Okay, therefore, this is a kind of broader definition for these layers. Again, I'm going to come and bother you at the beginning of each chapter what data link layer is, what physical layer is, what network layer is, what transport layer is, and at the end of the day, what application layer is. Therefore, here, this is the one that we are going to focus on, the hybrid model. The hybrid model is the one, this is what we follow. Okay, and as far as our definition is concerned, we are going to have the following encapsulations. Okay, is there a possibility to change the text color? Let me try to see. No, no. Yes. Okay. Therefore, application user provides protocols that provide network services to user programs. Transport layer assures end-to-end data integrity. Network, inter-network addressing and routing. Data link, provision of network technologies in order to provide media access, hardware addressing, etc. And physical layer to assure the digital bit transmission. This is what it is. Then, for the sake of our understanding, we are going to say something about data encapsulation. Therefore, if you have data from the user program, when it reaches the application layer, it is still called datagram. Sorry, data. And as a transport layer, we are going to call it datagram or segment. Okay. Remember, datagram or segment, it is either for TCP or UDP, but you are going to understand it. Both are synonymous. Then at the network layer, we are going to have a definition for packet. As the data link layer, we are having a definition called frame. At the physical layer, of course, we have a definition called bit. These are important higher level thinkings that I want you to remember. And of course, as I promised, by Monday, Tuesday, I'm going to compile all the notes that will give you some further reading on these issues. No problem. But at least in order to go forward, we need to understand what is defined at the higher level. Let me pause for 30 seconds here if anybody has got a question. Anybody with any question? Okay. Therefore, now let's continue with, if we can, I don't know. Let's stop the annotation. I hope the PowerPoint is going to continue. Yes. Okay, but for the purpose of clarity, I need to delete all the annotations. I think I better stop sharing and start sharing. That's a better thing instead of deleting those. Okay. Now remember what I said in the previous slide. Okay, in the previous slide, I said the lowest two technologies, these two guys, are infrastructure. And part of the network aspect is also mainly infrastructure. There is so much marketing here. Network card manufacturers, cable manufacturers, connector manufacturers, patch panel manufacturers. I'll tell you about structural cabling as well. The computers themselves, the operating system manufacturers, all these kind of competitors are out there. We are living in a good time now. But if you happen to live like 30 years ago, there were some companies who tried to hijack the entire network industry, forgetting about the open nature of it. Therefore, imagine a company called IBM monopolizing everything on you. Therefore, what happens was, yes, there is the physical aspect. This is a good example that I always use. Imagine there is an artist, let's say Mahmoud Ahmed, is releasing a CD. Then, in order to listen to Mahmoud's music, you need to buy a specific CD player. Okay. Then the longest has also released another CD. Then you are going to buy a different player. If that is the scenario, do you think you are going to cope up? You can have as many CDs as you want, but you cannot have as many CD players as you want. Therefore, the whole concept is, let's have the same hardware, if there is a router also here, the same hardware, supporting different protocols. Nobody is going to attach you to TCP IP only, but IPX, SPX can run, AppleTalk can run, or any other protocol, NetBU can run, or any kind of protocol can run on top of that. Therefore, that interfacing is possible. It is an open interface. A human being can be a secretary. A human being can be a salesman. A human being can be a teacher. A human being can be a nurse. A human being can be a doctor. Yes, but at the end of the day, there is a human being. But you can say different paths through an interface called learning. Through that interface of learning, you can actually acquire so many things. Therefore, yes, once we make this standard open, there is no problem in supporting multiple protocols. But if we make these underlying things closed and proprietary, we are ended up in a problem. Therefore, the lowest two layers have got so much potential for standardization. If we fail to do so in standardizing those, we are going to end up in creating a monopoly of hardware manufacturers that are going to affect the user. Therefore, the ISO gives this standardization project to the Institute of Electrical and Electronic Engineers back in the year 1980. This is the second month of February. so that these standardization numbers are going to proceed. Okay. Dot 1 is about, for example, spanning tree protocol. Dot 2 is about logical link control. Dot 3 is the one that you know today as Ethernet. Dot 4 is token bus. Dot 5 is token ring. All of you know about 802.11, that is wireless LAN. 802.16 is Bluetooth. 802.17 is WiMAX. There are so many standards. Some are dead long ago. For example, forget about these guys, they are dead. Forget about these guys, they are dead because it's no more being used. Think about these guys, they are still evolving. Think about these guys, they are still evolving. You know about 802.A, B, N, G, all these kind of standards are there. And for IEEE 802.3, we do have so many standards. But what is the rationale here? The rationale is not for you to remember which number is which, no. The rationale here is, unless we standardize the basic infrastructure aspect of networking, we will end up in monopoly. Let an organization standardize it and let manufacturers follow those standards in order to give us actual devices. Therefore, the specifications for Ethernet, that is the network you all know, including switches, including hubs, including bridges, including cables, including connectors, including computer network cards, including every aspect of it, is standardized by these guys. What is the media access technique? You will learn about CSMACD in chapter 3. What is the hardware addressing scheme? You are going to learn about the 48-bit hardware addressing. Okay, you are going to learn about flow control. How can we manage speed? What is 10 megabit per second Ethernet? What is 100 megabit per second Ethernet? All these kind of details have been facilitated by the standards of IEEE 802.x. Therefore, when you are looking at these guys, they will give you the broader picture. When you are looking at these guys, they will give you the granular aspect of the lowest two layers of the OSI model. Then as far as we are concerned, of course, we are going to mention a lot about 802.3 and 802.11 in their respective chapters. 802.11 in chapter 7 and 802.3 in chapter 3. We are going to mention them. However, you need to understand why the appropriate 802.x standards come into existence. Okay, for example, 802.x says, let's have this thinking. Okay, instead of having, this is data link layer, remember? And there is a physical layer. And therefore they say, let the physical layer be there. Physical layer specification can be given. But the data link layer that has been won in the other models, it is going to be divided into the media access control sublayer, MAC, okay, and the logical link control sublayer. The very presence of a logical link control sublayer facilitates driver specific or software specific kind of communication to the higher layer protocols. In chapter 3, I will mention two things. One is called NDIS, the network driver interface specification, and the other is called the Open System Interconnect. The NDIS, the network data interface specification. Okay, we are going to mention them in such a way that how they can help us interface to the higher protocols. Had there not been LLC, this interfacing is going to be difficult. Therefore, LLC clearly identifies, most of it is provided by network driver specification, how we can interface to the higher protocols. Again, the lowest two layers remain somehow tied up with hardware. Therefore, what you can actually see in most of the definition is the physical layer and the MAC layer, which are going to be facilitated by the logical link control sublayer. Therefore, again, I'm going to provide you documentation on this, but when I provide you documentation on this, it is not for you to memorize any of those, but understand the rationale why we are going to have those standards. Okay, I call them standards. I didn't say reference models. Some books are calling them reference models. Reference models gives you the theoretical background, the theoretical functional definition. But standards, they are actually specifications about the manufacturing of certain aspects of that particular layer. Okay. Therefore, this is how the two fit in the discussion. Therefore, this is the first bullet point in chapter 1. Again, let me pause for a little while. For the sake of the file size, I usually take 1 hour and a half or maximum 1 hour and 40 minutes. Otherwise, the file size is going to be getting bigger when I upload it. Therefore, now we are going to finish maximum in the next 15 minutes. Therefore, bear with me. Any question you have? Am I rushing? Am I sluggish? Any volunteer?
I think your pace is fine. So
good. Yeah. Thank you, Abtam. Thank you, Mike. Thank you. Okay. Good. Now let's begin something which is going to bother us again and again and again and again and again in all our discussions, at least up to finishing chapter 4. Okay, the idea of collision and broadcast domain. Therefore, before I open the slides, okay, some of the pictures available in there, let me try to give you a highlight. Okay, thank you, Beza. Therefore, here, imagine. Okay, the very good question to raise here is the following. Which one do you think came first? Networking or standalone computing? I need an answer, and I need a consensus among us. Which one do you think came first? Anybody, you are welcome. You can speak. Unmute your mic and you can speak.
Standalone computing.
Standalone computing. Okay, who said that? Batra, good.
Better.
Okay, Batra said standalone computing. Anybody arguing against? Okay, I'm going to argue against Batra. Okay, first we had networking, unfortunately. Okay, why? Because of cost. Look into history. Google Arguna, when movies like Pirates of Silicon Valley or movies like Triumph of the Nerds. Try to look at such kind of movies. I think they are freely available on YouTube nowadays because they are very old movies. Just try to look at them. Once upon a time, computing comes. But remember, computing was so expensive. Yeah. Therefore, we have either what are known as mainframes, yes, or mini computers. Sorry, nowadays we have got microcomputers. Therefore, we have got mini computers that serve multiple people. እኔ ትንሽ ሽማግሌ ስለሆንኩኝ እነዚህ አይነት ማሽኖች ለማየት ደርሻለሁ. Most of you, I don't know. Okay, some 20 years back, commercial bank used to have a mainframe. Okay, and what it has got is kind of dumb terminals. At Sabah University, they used to have such kind of things. Therefore, now, this is very expensive. One, it is too big. Two, initial price of it itself is really big. Three, it takes so much power. But most of all, it is so slow. Okay, I remember touching a hard disk equal to a normal chair size that has got 200 meg storage capacity. Can you imagine that? Okay, a hard disk equivalent to a chair that is only 200 meg. But that was the technology. Okay, therefore, this was too expensive. And the only thing that you can do is you are using dumb terminals. Okay, what is dumb means? They are dumb. They don't do anything. They don't do any processing. They share the time of this mainframe thing. Therefore, እዚህ ጋር Mr. A ከተቀመጠ እዚህ ጋር Mr. B ከተቀመጠ both Mr. A and Mr. B are using the same mind. Okay. Therefore, think of it like a Hindu goddess with multiple hands. Okay. Therefore, so many hands, but just one brain. Therefore, this was so bad because you are sharing the time of this the centralized processing engine here. When you don't have the connectivity, when you go home, you cannot have connectivity to this one. You need to come to certain locations in order to access this one. But while on this mainframe, while on this mini computer, Mr. A and Mr. B can send messages. That is the whole idea of networking. Mr. A and Mr. B share resources available here. Maybe a printer is attached here, a teletype printer. They can share resources here. Mr. A and Mr. B may access the same financial application here. Therefore, the whole concept of networking that you can imagine, okay, has been prevailing here. But one thing is so bad. What is that one thing which is really bad? Okay, here is network with centralized processing. That is so bad. You have got only one processing aspect, and if it dies, everything dies. Therefore, this model of networking is not something we are going to appreciate. The network model that we have today is called a client-server paradigm. Therefore, what happened? In the late 1970s, okay, in early 1980s, some kids started envying the mainframes. They just had a motto. They say a mainframe on every desk. That was the biggest motto ever achieved. Had it not been the case, of course, today you are not going to study computer science, I'm sure. And who are these kids? Most importantly, Steve Wozniak, the founder of Apple, Steve Jobs, the other founder of Apple, Ed Roberts, the founder of another company called MITS, Bill Gates, you know all of course, Bill Gates, the richest man today, or I don't know, he's the richest man. And you have got things like the colleagues of Bill Gates, like Ballmer and the other people. They were really envisioning about having a mainframe on every desk. What does that mean? We are going to need a miniature mainframe. In order to have a miniature mainframe, what do you need? We are going to need a small hard disk. We are going to need small processors. We are going to need small memory. We are going to need small elements that can be cheap enough in order to fit into this. And luckily, that revolution brought the first Apple computer, Apple II. I don't want to teach you history here. Apple I is the first personal computer. Then, of course, Apple II. And the success of Apple made IBM really envy Apple's success, because IBM is a manufacturer of mainframes. When IBM came to the PC industry, they chose to assemble computers instead of starting from scratch. Of course, today, Apple is also using Intel processors, but back then it was proprietary. Therefore, here they decided to assemble. What did Apple create in the first place? They created the BIOS. What is the purpose of the BIOS? It integrates operating system from Microsoft called DOS. It integrates memory from a company called, let's say, Livingston. Of course, the original computers didn't have a hard disk, but integrate a floppy disk from another manufacturer. But as the core of it, there was a BIOS. But once that is discovered, reverse engineering is becoming possible. Therefore, we are lucky enough today, we have got all sorts of IBM compatible computers. Now, you know, the IBM PC wing is sold to a Chinese company. And what is the name of the old IBM? It's called Lenovo. Yeah. Therefore, Lenovo is former IBM personal computer stuff. Therefore, now we are lucky enough to have all these personal computers. Therefore, thanks to those people, we are having, okay, a personal computer revolution. You have been saying my word perfect, my Lotus 123, my word processor, my this computing, my game. You are doing all these kind of issues. Okay, therefore purely personal computer. And what is being done here? What is being done here is basically only front-end processing. Okay, therefore this becomes front-end processing. Then there comes an idea. You have a printer. I don't have a printer. Can I share your printer? How? Okay. I want to send a message to you. Instead of bringing on a floppy disk, I want to send it directly over a communication channel. Because people had enough. Okay. Because in the old days, people used to connect one another. Now in the new era, we lack that connectivity. Therefore, how can we reinvent the whole idea of networking by bringing some ideas from here to here? Therefore, now there comes an idea of connectivity. Okay, let's connect one another. Let's connect one another. Okay. And this actually gave way to the network as we know it today. What is the name of this network that we know today? It's called a client-server paradigm. And what is the effect of this? Processes are divided between front-end and back-end. That is the whole idea. Maybe if the back-end is so much busy, you are going to have a dedicated server. But when you are browsing a website, there is a thing which is done by your back-end, and there is a thing which is expected to be done by the front-end. Therefore, yes, we are here now, as Batra said earlier, we are here now, but the whole idea began in this era, Now, just to begin this idea for our next discussion, things are not really smooth. Of course, the very first idea is, I have an intelligent computer, you have an intelligent computer, okay? Let's have a very stupid cable between the two of us. The intelligence of our two computers is going to take care of the communication. This is the first network, okay? However, if you grow in such a model, you are going to end up in a problem. One, the cable cannot be extended indefinitely. The signal will be weak and get lost. Therefore, you need a level of repetition. You need a level of signal clearing. Without that kind of level of signal clearing, you are not going to let everyone communicate one another. Then once you do that, maybe some aspects also may arise. Using your common knowledge, what you see here looks like a bus topology. And the so-called bus topology has got its own administration problem. Therefore, people invented two types of device in order to look into this problem. The first device is called simply a repeater. A repeater is weak signal, boosted for another length. Weak signal, boosted, make it ready for another length. Or you can have a multi-port repeater, okay, by the name, which is famous up to recently, called hub. Okay, and what happened? Okay, this particular thing is called a hub. Is a hub very important today? No, because hub has got very weak functionality, and of course, devices such as a switch are going to enable it. Therefore, in the next session, I'm going to make it clear. But the issues provided by such a network or the solutions provided by repeaters, okay, or the issues provided by hubs didn't resolve a very important terminology, which we call collision management, collision segmentation. Despite the presence of all these, we are going to have one collision domain. What is the meaning of one collision domain? Where you fight for the resource. This is a good example. You are driving from Bole to Mescal Square, okay? Whose road is that? Everybody's road. In a crowded day, you should be crowded there. If the road is empty, you are going to drive smoothly. Therefore, you are going to share that resource equally. There is no differentiation among any of the drivers. Okay? But what if, let's say, it's just an example, the Prime Minister is coming from Boli. First of all, what will happen? Okay, the road will be cleared for his entourage. Yeah? Therefore, that road is now being his and his alone. Therefore, if they are driving at whatever speed they are going, they can do. Are they worried about colliding with someone else? No. Why? Because the road is empty and it is theirs and theirs alone. Therefore, if there is a place where all the nodes equally fight for a resource, that area is called collusion domain. At this initial stage of networking or at physical layer, the one thing you can do is define one collusion domain. If you are in a network where each one of you listen one another a broadcast, okay, then that defines a broadcast domain. A broadcast domain is possible if one thinks of hierarchical addressing. A broadcast domain is possible if one thinks about routing devices. But I'll differentiate that. Therefore, let me share these two pictures with you before I stop. Next class, we can continue from there. Okay, I think I have to stop the. Can we see the pictures? Let's try. No. Therefore, to avoid yeah, I don't want to keep. Oh. Now I'm opening the normal PowerPoint, and this is a particular slide I'm interested on. And now coming to the share. Sorry about that. I am going to use this. Therefore, these are the two pictures I want to show you. One is to define, come on. One is to define, what's happening? My slideshow is not going, okay, good. One is to tell you about what we call collusion domain. Okay, I'll explain it very clearly because this is very important to understand at the beginning of next class. And the other is the definition of broadcast domains. Don't worry, you are going to understand them. But for today, it is better to stop here. 1 hour and 40 minutes is more than enough. If you have any questions, I can pause. Maybe I can check your chat if you have any questions. Anybody with any question, you are welcome to ask. Okay. Therefore, remember again, I'm giving you the very broader generic definitions. And even if some things are blurry for you at this point, they are going to become clear when we reach those individual chapters. And as I promised, by Monday or Tuesday, I will compile all reading materials to you and I will post them in the Google group together with selected questions for our revision. Therefore, next class, my plan is to tackle this idea of collusion and broadcast domains briefly so that you can have that broader understanding. Then we can go into a question and answer session where I bring up certain topics based on the questions. Therefore, each topic is going to be revised accordingly. Then, of course, through that revision, we are going to see the level of understanding you are having for those issues. But for today, I will stop here. I think I have a question here. Okay, Habtam, your question, I think I'm going to repeat it if I'm saying. Did I hear you say LAN is not configurable? I just wanted you to shed light on this. Good. Therefore, think about building a LAN. Okay, you are thinking about building a LAN, having a computer with a network card, having a switch, having maybe a wall outlet, having a cable, having a connector. Okay. Whenever you deploy all these things, have you ever asked in a shop, you go to a shop, and have you ever asked, give me an Ethernet switch, give me a computer with an Ethernet adapter, or a wall outlet that supports UTP cables that supports Ethernet? Have you ever asked that, Abdul?
Actually, I've never done any of this. So
okay, therefore, when you go to, very good, when you go to a shop, you are going to buy and deploy a network technology. That's what I meant by non-configuration. Of course, at the end of the day, on the computer, you are going to configure IP address. Okay, that's layer 3. But until you brought the switch or the computer to your premises, you are on layer 1 and layer 2. Therefore, layer 1 and layer 2, you buy and deploy a technology. You are not doing the configuration. Once that technology is deployed, you start doing configuration from layer 3 and above. You take for granted layer 1 and layer 2. Okay, they are things you can buy and deploy. They are not things that you are going to configure. Okay, how about now? Is that clear? Therefore, instead of saying LAN, say it layer 1 and layer 2.
Okay, that's clear.
Clear, Rahul?
Ah, good. Thank you.
Good. Any other question you may have? Good, thank you. I think the participation is also very encouraging. I have 21 students participating today. The class size is around 30. Therefore, please encourage your colleagues also to attend. And feel free to raise any kind of questions as much as you can. And I will continue from where I stopped on Wednesday, but in between, I will post the materials as per the need. Thank you for your attention and have a very restful weekend.